Now, collisions in 2D. All right, this one is still talking about collisions. This is actually a new addition to your syllabus since 2016. If you look at questions before 2016, you don't have any questions on 2D collisions. Okay, it was only added after 2016. It's a new recent addition to your syllabus. Now, what is collision in 2 dimensions? Collision in 2 dimensions is something like this, where we tell you that you have one object that hits another object, and then after collision, instead of moving in a straight line like this, where maybe this one moves in a speed like this one is considered to be 1D collision, where momentum is only in one direction. Okay, so instead of having a case that looks like this, where both still move off in one straight line, it could be that after collision, one of the object moves here in this direction, one of the object moves here in this direction. You see, they are no longer moving in a straight line. Okay. Previously, all the examples you've done, your objects were all always moving in a straight line before and after collision. If you have a case where after collision, they don't move in a straight line, they move in different directions like this is what we call as 2D collision. Okay. Now it's called 2D because it involves momentum in 2 different directions. What do I mean by that is that if you recall what you learned under vectors, remember I told you if you have a particular vector like a force that's diagonal, that force can be resolved into 2 perpendicular components, one that is fx and one that is fy. So this force F that you have here is actually produced by a combination of 2 different forces in 2 different directions. What I meant by that was that fx drawn head to tail, fx and fy drawn from head to tail will give you back the f here, right? So here, this force is actually produced by a combination of force in 2 different directions. Okay, so it's something similar here right now. This momentum that you have here is actually produced by momentum in 2 different directions, namely a momentum in this direction and a momentum in this direction, in the x and y direction. The momentum in the x and y direction is what gives you this diagonal momentum here. So that one is just the background of it. Let's just go through the actual contents here. Now, for any 2D collisions, total momentum in any direction is conserved. Okay, so 1D collision is where momentum is only in one direction. 2D collisions would have momentum in 2 different directions. Okay, so here what we'll tell you is that in those different directions, the total momentum in any direction must be conserved. So the example that we will give you here is this. An object of mass small m is moving horizontally when it strikes another stationary object of mass capital M. After collision, they move off in different directions at the angle of alpha and beta, producing momentum in different directions. One momentum here and one momentum here. Okay, so as I mentioned to you, their momentums can be resolved into 2 perpendicular components. So what you have is that you could have a momentum in the y direction and x direction for this. You could also have a momentum in the y direction and x direction here. So conservation of momentum will still apply here in this case. But now we will tell you that the total momentum in any of the specific direction must be conserved. What we mean by that is that if you consider the y direction alone, the total momentum must be conserved. If you consider the x direction alone, the total momentum must also be conserved. Okay, so here I say that although there is momentum in different direction, the total momentum in any direction must be conserved. What this means is basically these two statements here. I'll just go down a little. What this means is that when total momentum in any direction must be conserved, it means conservation of momentum in the x direction. Sum of initial momentum in x direction is equal to sum of final momentum in x direction. It will also mean conservation of momentum in the y direction, where we say that the sum of initial momentum in the y direction is equals to the sum of the final momentum in the y direction. Okay, that is what total momentum in any direction means. So right now, what we want to do is that we want to consider the momentum only in specific directions, x and y. So if I look at this diagram right now, this is actually the before case, and this is actually the after case. Okay. Now, what if I consider the x direction only? This momentum before collision, it will just be mu. Okay. It will just be mu. If I consider only the x direction or the horizontal direction, the momentum of this small m here is just mu in the horizontal direction. What about the momentum of the big M here? There's no momentum here for this one because it's just stationary. The momentum in the x direction for this before collision is just going to be 0. Okay. Now, after collision, these two objects, the small m and big M, move on in different directions. So I want to analyze it in two specific directions only. So I want to analyze it in both the y and x direction. I analyze it in the x direction now. This momentum here can be resolved into x and y direction. But to find the momentum in the x and y direction, I need to resolve something. So the mass is a vector. The mass is a scalar. I cannot resolve mass. But speed is a vector. I can resolve. Sorry, velocity is a vector. I can resolve the velocity. So right now, what I can say here is that this one can be resolved into two perpendicular directions. I said that if this one is angle alpha, this will be angle alpha here. So this one will be u over 3 cos alpha because it's adjacent to the angle. Whereas this one, if I shift it here to complete the triangle, it will be opposite to the angle. So it will be a sine. So this one is u over 3 sine alpha. Likewise, if I look at the one at the bottom here, I can resolve the velocities into two perpendicular directions so that I can get momentum in two different directions. If this is angle of beta here, this will be angle beta 2. All right. This part here is adjacent to the angle. So it will be u over 2 cos beta. And then this one, if I shift it here to complete the triangle, it will be opposite to the angle. So this one will be u over 2 sine beta. Okay. So since I'm only considering the x direction or the horizontal direction, I only consider the momentum in the x direction here, which means to say I only want to consider this one and this one. The momentum for these two. So if I talk about the big M, the momentum will be the product of the mass and velocity in the x direction. It will be m times u over 3 cos alpha. And then if I talk about the small m, if I'm only considering the momentum in the x direction, I take the product of the mass multiplied by the velocity in the x direction. It will be m times u over 2 cos beta. This one here is the total momentum in the x direction. So far, so good with this. Can you follow now? Up to here?
Yeah.
Okay, you are actually adding up the momentum in the x direction only.
Yes.
So if you see any diagonal momentums, you're supposed to resolve it into two perpendicular directions, both in x and y. Okay, so this is you considering conservation of momentum in the x direction. So the next one you will do is to consider conservation of momentum in the y direction. This is for the vertical case. All right. So we repeat the analysis again. Now, if we look at the case before collision, the total initial vertical momentum is actually 0. Because you see, this one here was horizontal only. This object here was moving perfectly horizontal. There is no vertical component. It's only horizontal only. Therefore, no vertical momentum. And then needless to say, this one is also stationary. There's not going to be any momentum. So obviously your total initial momentum would be 0. There's no vertical momentum whatsoever. One of it is just horizontal only, one of it is stationary. So the initial vertical momentum is just going to be 0. But then when I move on to the case after collision, because I already resolved the velocities here, so my work here is a bit easier. If I want to find out only the vertical momentums, for big M, I take the mass multiply with the vertical velocity. For small m, I take the mass multiply with the vertical velocity to get the momentums. Okay, now, when you add this one here, this is where you need to be careful a little. Remember, I mentioned to you that when adding or subtracting vectors, you need to be careful about the directions. There is always a sign convention that you need to take into account where you assume one direction to be positive. Now, in the previous example here, there's no issue because you see both of your masses were moving in the same direction. They're not moving in opposite directions, so you can just simply add them up. There's no negative to consider. But right now, you will notice that this one is going upwards. This one is going downwards. So this one has opposing momentums. When you add them up, you need to assign one of them to have a negative. So let's just say going upwards is your sign convention. This one here would be negative momentum. This one here would be positive momentum. The ones that you see here is actually your sign convention. And this is your sign convention. Okay, so if I talk about the big M alone, the momentum will be big M multiplied with U3 sine alpha. Okay, it will be M times U3, U over 3 times sine alpha, and it will be positive. But when I talk about the small m, the momentum vertically would just be M times U over 2 times sine beta. But because it's opposite to my sign convention, it will be a negative. That's why there's a negative sign here. Okay, so this is you adding your momentum in the vertical direction. Okay, now the way you add up your momentum is actually the same as the ones that you did previously under 1D. The same rule still applies. Okay, it's just that now under 2D momentum, you consider two different directions only. Okay. So far, still okay, right?
Yeah.
Okay. All right, so this is 2D momentum, you adding the momentums together in both X and Y direction. All right, so whatever I just explained to you here is actually written here already. All right. Okay, then after that, there's just one thing I need to mention. Let me just clear everything off. Okay. Yeah, the last statement here, I just mentioned this to you. There's this statement here. Total y direction momentum is conserved since initial momentum before collision is 0, which is this one. Masses m and small m and big M each gain equal but opposite momentum in the opposite in the y direction. Okay, so what will happen is that because this one is 0, this one by right after collision must also be 0. The only way that this total will be 0 is if this is equal and opposite. I mean, from this equation here, you can actually very easily see that mu over 3 sine alpha is equals to mu over 2 sine beta, therefore equal opposite. Okay, that's what this statement here is talking to you about. All right, so this is one part. Okay, now in a vector diagram, momentum vectors of small m and big M after collision add up to equal to the momentum F before the collision as shown. Okay, now this is something else. This one is in vector form. Okay, I'm talking about if they are in vector diagram form. Maybe it will be easier if I show you this. Okay, now if I look at these two diagrams right now, before and after, let's just say right now I just don't want to resolve them into any direction. I don't want to calculate it in any direction. I don't want to resolve it. I don't want to do any calculation. I just want to know what is the momentum as it is in one direction. If I look at this one, my momentum here for this one would just be mu going in this direction. You know. If I just draw a vector arrow for the momentum here, this one will just be mu. Okay, this one has no momentum. If I draw the vector arrow for the momentum under collision, this one will just be in this direction. This one will be mu over 3 at the angle of alpha, whereas this one would be mu over 2 at the angle of beta. Okay, this one is the vector arrows for the momentums as it is. Now I'm not resolving the vectors. Okay, what I do know is that momentum is conserved. Okay, so sum of momentum before collision is equals to sum of momentum after collision. In vector form, here, this is the part where it gets a bit difficult to explain. In vector form, so our initial momentum is equals to the sum of final momentum. Let me just write this out properly. In vector form, this means that mu is equals to mu over 3 plus mu over 2. Okay. Now this one I had to do a bit about, I have to revisit a bit of your chapter 1. Okay, now let me just give you an example again from your chapter 1. Do you recall the difference between this? If I have a vector A, and then I have a vector B, vector A, vector B, vector A and B drawn from head to tail will give me a resultant vector, right? If I say that this one is 3, and then I say that this one is 7, sorry, if I tell you that this one is 3 Newton, and then I tell you that this is 7 Newton, okay, now maybe I do it this way. Maybe this is easier to see. This one is vector A, vector B. This one is 4 Newton. This one gives me a resultant like this, whose value is 5 Newton. Okay, so this one is just something like to test your understanding of maths a little. Now, in vector equation form, is it correct to say that vector A plus vector B will be equal to vector R? In vector equation form?
Yes.
Yes, correct. That is correct. But if I write it as in number form, in magnitude, if in magnitude only.
Because 3 plus 4 is not 5.
Yeah, if I just write in magnitude only, where I say that 3 plus 4 equals to 5, this one is very wrong, right? Correct? There's no such thing as this, right?
Yes.
So the thing that I'm trying to do now is that what I'm trying to explain here is that it's something similar for this also. Because you see, if I have if I talk about vectors, vector A plus vector B will give me vector R. This one is actually correct. But if I just say that the magnitudes of the vector added together will be this one is definitely wrong. Okay, so it's something similar here right now when I talk about the conservation of momentum for 2D collision. I know that the sum of initial momentum must be equal to the final momentum. So right now, if I talk about in vector equation alone, in vector equation form alone, the momentum before collision is just going to be mu, denoted by the arrow here. Okay. It's just going to be mu. But the final momentum after collision will just be mu over 2 plus mu over 3. Now, this one is considered to be correct. All right, in vector equation form. So if you recall what I mentioned to you last time in your chapter 1, I said that vector A and B drawn from head to tail gives R. So you have something similar here right now, okay, where we tell you vector mu plus vector m over 3 and mu over 2 drawn from head to tail gives mu itself. Okay, similar. So what you're gonna get is this one here. You see, mu over 2, you already know is this one. Maybe I match it with the color. It's this one. Mu over 3 was this one. So you draw them head to tail, you're gonna get this, right? Then these two drawn from head to tail will give me back mu itself, which is this one. Okay. That's why here I wrote here in a vector diagram form, momentum small m, big M after collision add out to be equal to momentum F before collision as shown here. So far, so good.
Yeah.
Okay. So this is if it is talking about in vector diagram form. Okay. Yeah, this one here, maybe I need to add another thing. Yeah, from here, in vector equation form, this one is correct. In magnitude only, I cannot say that magnitude of vector A plus magnitude of vector B will be equal to magnitude of vector R. This is wrong. Okay, this is very wrong, not valid. Okay, only in vector form is this going to be valid. Okay, so just bear in mind this one first, because there's one question later that relates to this, where you need to know the difference between these two. Okay, so this is 2D collision. So we just do one question and then another 2 or 3 before you can end this lesson. Okay, if you look at page 11, we did not do one last question there. You have a 7 kg object that is moving at 12 meters per second to the east that explodes into 2 unequal fragments. The larger 5 kg fragment moves 15 meters per second to the south. Determine the velocity of the smaller fragment. So you have a 7 kg object moving at 12 meters per second towards the east, and then it explodes into 2 unequal fragments. This fragment and this fragment. The larger 5 kg will go towards the south at 15 meters per second. Find out the velocity of the smaller fragment, which is actually this one. Okay. Now, since this one you know is 5 kg, the other remaining one ought to be 2 kg because the original is 7 kg. Okay, so this one we just solve this one first. Okay, now because this one you see the momentum isn't in just one direction. There is a diagonal momentum here. There is actually momentum in the x and y directions. So I need to use what I did just now. Conservation of momentum in x and y direction. So since this is a 2D collision example where I have momentum in x and y direction, I use conservation of momentum in the x and y direction. So right now, if I say conservation of momentum in x direction or horizontally, sum of initial momentum is equals to the sum of final momentum in the horizontal direction. So now let's try to add up the momentums in the x direction. This is the before, and then this is the after. So for the before case, I'm only gonna have 7 kg times 12. There's nothing else to consider here. But what about after the collision? So now you see these vectors here, the speed, the velocity here specifically, there's one over here that I can resolve. specifically this V here. I can resolve this to, since this is angle theta, this is V cos theta, this will be V sine theta. Okay. For the 5 kg fragment, there's nothing to resolve. It's perfectly vertical. I don't need to resolve. Okay, this one, no need to resolve since it's vertical only. Okay, so if I talk about the horizontal momentum or the x direction momentum only, I only need to consider this one, the momentums with speed of v, the momentum caused by a speed of v cos theta. So to get the momentum here, I take the mass multiply with the velocity in the x direction. This one will just be 2 times v cos theta. The 5 kg fragment, there's no horizontal momentum because it's only vertical. So this one, I don't have anything to write. So I will only end up with this equation here. So now what I have is 2v cos theta equals to 7 times 12, giving me 84. Now you see, I cannot proceed any further because there are two unknowns. I don't know angle theta, and I do not know angle. I do not know angle theta, and I do not know what is the velocity v. So I cannot solve this equation right now as it is. I need another equation to be able to solve. So this is where you consider the momentum in the y direction. So I'll write it at the top here. In green color. So this time I consider conservation of momentum in y direction. This is if I'm talking about it vertically. So sum of initial momentum is equal to the sum of the final momentum vertically. So now let's consider the momentum vertically before collision. Now here, this one has only horizontal momentum, no vertical momentum, because you see that it's only moving horizontally, right? So this is just going to be 0. But what about after collision? Now after collision, this is where you can have two momentums. The first one is caused by this one, v sine theta. The second one is caused by this one, the 15 meter per second. All right. So now you have two different momentums here, this one and this one. But now when I want to add them together, because they are in two different directions, one of them must be negative. Okay. So let's just say that I have upwards as positive as my sign convention. So this one will be positive. This one will be negative. So my momentum here is 2 times v sine theta minus 5 times 15. So I'm going to end up with 2v sine theta equals to 5 times 15, giving me 75. So this is equation number 2. All right. So now how do you then proceed is that you see this is v sine theta, this is v cos theta. If you take one divided by the other, it will give you a new trigonal relationship. If I say that 2 divided by 1, this one is another part here, okay? If I say I take 2 divided by 1, it will be 2v sine theta over 2v cos theta 75 over 84. The 2 will cancel off, the v will cancel off. Eventually, I get tangent theta equals to 75 over 84. So 75 over 84 arctangent of that, I'll get theta equals to 41.8 degrees. Okay, but this is not yet complete. They want the velocity, right? So right now, what you can do is you either choose equation 1 or you either choose equation 2 to find the V. It doesn't matter which one you use, but let's just say I use equation 1. From 1, 2V cos 41.8 equals to 84. V is therefore 84 divided by 2 divided by cos 41.8. I will get 56. You know, 2V cos 7 times 12. 84 divided by 2 divided by cos 41.8. I'll get 56.3 meter per second. Okay, so this is what I'll get. This is the final answer. This is the velocity for the smaller fragment. Okay, by using conservation of momentum in both the x and y direction. So far, so good. Can 75 divided by 4 tangent that. Okay, so is this okay? So far so good.
Yeah, hold on. Let me copy the last part.
Okay, right, no worries. Just trying to do this a little. Yeah, this is actually the last part of dynamics. This is probably the one that is the most confusing for the entire chapter. Actually, if anything, some people would do their workings like this now. Where they say that V cos theta is actually 84 divided by 2. Sorry, 4 divided by 2, giving them 42. And then this one they say is V sine theta 75 divided by 2, giving them 37.5. So some people may have tried to simplify further to become this, where they just say this equation divided by this equation gives me the same answer. Okay, it doesn't matter which one you use. You can still do either one also. Let me just say all this. Okay, can?
Yeah.
All right, so this one is okay. Then let's just look at some 2D momentum questions with the time that we have left. Concept-wise, we've already gone through all your dynamics chapter. What we are left now is just to do more examples. Okay, now if you look at page 13, which is this one. Now, a particle of mass small m traveling with speed u collides with a stationary particle of mass big M. The velocities of the two particles before and after collisions are shown. Which vector diagram correctly shows the momenta before and after the collision? Okay, momenta is still the same as momentum. It's actually the plural form of momentum. Okay, it isn't any new term. It's just the plural form of momentum. So this one is the same example that I just gave you inside your notes. So as I mentioned to you, whatever you have here, if you just look at it in terms of vector diagram, before collision, you have a momentum in this direction. And then after collision, you have momentum in this direction and in this direction. This one was just mu. Okay. This one was just mu. This one was just going to be m. I have different color. This one is, let me just get rid of this. This one is mu over 3 like this. This one is mu over 2 like this. So in vector diagram form, if I know that sum of initial momentum is the same as the sum of the final momentum, in vector diagram form, I will know that mu is equal to big mu over 3 plus small mu over 2. So your answer for this would have been answer, which one do you think it is? A, B, C, or D? Basically, this one is just telling me vectors big mu over 3 and mu over 2 drawn from head to tail gives mu. So the one that you would get is actually answer choice B.
Yeah, is it B?
Yep. So this one is B. Okay. So this is the correct one. Now let's look at page 16. Let me just look at page 16. Page 16 will be 3 pages away. Okay, now let's have a look at this one. Okay, now you have a ball of mass m traveling at velocity u that collides with a stationary ball of mass capital M. After collision, the two balls travel at velocities v, small v, and big V respectively in the direction shown. A student writes 3 equations relating to the collision. Which row in the table indicates the correct and incorrect equations? Okay. Wait, let me just, this is page 16, yeah. Now, which are the correct and incorrect equations? If let's just say I give you the equations in the x and y direction, let's just say right now I write it out for you, x direction. Before collision, this one would just be mu plus 0 equals to, this one you know you can resolve it into v sine 30, v cos 30. This one you know you can resolve it into v sine 40, v cos 40. All right, so back to the momentum in the x direction. This one would just be mv cos 30. This one would just be plus mv cos 40, right? So this one would in turn just be equals to mu equals to mv cos 30 plus mv cos 40. Now, is this equation correct? It should be correct, right? I mean, you can't see it properly here. This is actually oh, sorry. The V is also different, right? This is big V. All right. This is the big V. Let me just erase this. The problem with this question is that they use the same alphabet, but then it's mu equals to mv cos 30 plus mv cos 40. That is actually this one here, right? So it should be correct. What if you talk about the y direction? Now you talk about the y direction, there's no vertical momentum here because this one is moving horizontally, so no vertical momentum. This one is stationary, also again no momentum. So this one is just going to be equals to 0, right? But what about the vertical momentum after collision? This one you take small m multiplied with v sine theta. So this one will be mv sine 30. And then this one will be, you take the big M multiply with v sine 40. So this one will be negative because this one was momentum in this direction. This one was momentum in this direction. If you assume your sign convention is upwards positive, this will be negative. This will be positive. That's the reason why you have the negative here. So this one you get mv sine 30 equals to m big V sine 40, which will in turn be equals to what you see here. Okay. So this equation is correct. This equation is also correct. So if both equations are correct, you have two possible answer choices. It's going to be either answer A or D. All right. Now, this one is actually wrong because this is not vector equation. If the question wrote it in this way, if the question wrote it in vector equation form like this, if I apply what you just learned, the sum of initial momentum is equals to the sum of final momentum. This one will just be vector mu equals to vector mv plus vector mv. Let me write it out properly for you. This one will just be equals to mu plus mu equals to mv plus capital M this. Right? If your answer was written in this form, in vector equation form, then this one will be correct. Right? The ones here, you notice they don't have the vector notation on the symbols. All right. What this means is this. Let me just note this too. This one without the vector symbols, it is actually telling you this. Without the vector symbols, it means magnitude of mu equals magnitude of mv and mv added together. All right, that's why this is wrong. It must be in vector symbol for this one to be correct. So this one is out. The only answer choice you have is D. All right, because just now I talked to you about this, right? And then somehow in this question you see something similar again, but somehow this is not correct. The reasoning for that is because this is not in vector equation form. Okay, in vector equation form, you would have the little arrow here or some sort of other symbol to indicate this is a vector. In that sense, this one will be correct, but this is not. Okay, because without the vectors, some sort of vector symbol here, it means that the magnitude of mu will be equals to the magnitude of mv's added together. All right, it's something like this now. If in vector form, this is something that you learn, right? If I have a vector 3 Newton and then a vector 4 Newton, this one will give me 5 Newton, right? Let's say this is vector A, and then this is vector B, and then this is say vector R. Can I say that A plus B equals to R, meaning to say 3 plus 4 equals to 5? This is not possible, right? This is not in vector equation form, but if I write in vector equation form, vector A plus vector B equals vector R, then this is correct. All right, the analogy is similar here. Without the vector notation here, is saying that the magnitude of the vectors added together will give you this magnitude. This is wrong. Okay, right, that is what this question is about. Right, the diagram shows the path of the nuclei before and after after the collision. No other particles are involved in the collision. Which diagram is not possible? So here to emphasize to you, which of this is actually not possible? So what you have here is a case where this is a vector diagram of the collision before and after. Okay, they show you the path of the nuclei before and after the collision. So your guess could be that all this is the case before collision, and then all of this is the case after collision. So this is again something similar to a case of 2D collision, where we say that total momentum must be conserved in any direction, which essentially means that the sum of momentum before collision is equal to the sum of momentum after collision in X or Y direction. Maybe I just write horizontal or vertical direction. That one will be somewhat easier to see. In horizontal or vertical direction. Okay. So the fact is that we see that this thing here is this. Let's just say I look at question part A. I look at the answer choice A first. Now, what I can say here is that you see right now, if I look at this part A, the sum of momentum before must be equal to the sum of the momentum after in the x direction or the horizontal direction. That one is correct. Likewise, the sum of momentum before must be equal to the sum of momentum after in the y direction too. Now, specifically, you want to look at the y direction or the vertical direction now. Now, if you look at the case after collision indicated by the pink colored arrows here, these two can be resolved into two perpendicular components again, one here and one here, and then this one here and this one here. Okay, so if I ask you right now, the case before collision for the horizontal direction, this one will be non-zero, because you see now I clearly have something that is moving right now. So this one, initial momentum horizontally cannot be zero. Okay, because I have motion here. So if I have motion, there should be some sort of initial momentum. The initial momentum horizontally cannot be zero. So this one I know for sure. In the x direction or the horizontal direction, the momentum must be non-zero. After collision, it should also be a non-zero value. If I say that it was 5 Newton second before, it should also be 5 Newton second after. Okay, so now if you look at it right now, after collision, I have a momentum in this direction for both of the two arrows. Okay, you see, I would have one momentum here and one momentum here. Both of them will still add out to give me a non-zero value. So I could have a case where momentum horizontally is still conserved. So far you get to this, you get up to this point.
Yeah.
Okay. But now if I look at it in the vertical direction, the y direction, is there any momentum vertically before collision? If you look at right now, this case here, there's only horizontal motion.
There's no vertical
Yeah, no vertical momentum, right? So this one here, I know that there is no vertical momentum. Therefore, initial vertical momentum is zero. Sorry, maybe I just write this as this. There's no vertical motion. Therefore, initial vertical momentum is zero. Okay, so now I know that this one must be zero. Okay, the initial vertical momentum must be zero. So if momentum is to be conserved in any direction here, including the y direction, after collision, it must also be zero. Okay, so now if that's the case, you now look at the situation right now for part A. I see that there's one momentum here and there's one momentum in the opposite direction here, right? So it's possible that this can result in zero, isn't it? Because they are acting in opposite direction, they can result in zero, right? So in turn, this could mean that my momentum vertically is conserved. Correct?
Yes.
Okay. So this one here, this diagram is possible because it's telling me that momentum in the horizontal and vertical direction can be conserved. If I try to apply the same analysis for the subsequent diagrams, say for this one, for part B, I draw back again the arrow. I'm just going to skip some steps. This one is like this. This one is like this. So what I do see here is that total momentum is non-zero. This one, total horizontal momentum is non-zero. And then this one here, if I talk about the vertical one, total vertical momentum can be 0. So either way, I will still be able to satisfy this condition after collision. So B can also be possible. But now if I look at part C, okay, if I look at part C right now, I do the same thing as before. I try to resolve the momentums into two different directions, X and Y, horizontal and vertical. I get one here like this. Sorry. I do one here like this. And then I do another one for the other one. Like this. So I still have the same conclusion. Okay, sorry. Right? Yeah, Sonia, just now you log out later, right? You log out. No, you
Sorry,
just...
sir, the Wi-Fi.
Okay, right. No worries, no worries. Okay, I was talking about part C, where basically you are doing back the same thing. You resolve the momentum after collision into the X and Y direction, into the horizontal and vertical direction, which is represented by the blue and green colored arrow here. If you just look at the horizontal momentum here, the same thing you can see here that the total horizontal momentum is non-zero. So again, you could have this case. All right. But when you look at the vertical momentum, which is this one, you notice that in this case, both of the momentums are in the same direction. So you see here, both momentum is in same direction. So the total momentum can never be 0. All right. You see, because both momentum right now, the green arrow and the blue arrow, they are both pointing downwards. If you were to add them out, they will never ever become 0. If you compare with A and B, for A as well as for B, the vertical momentums after collision were both in opposite direction. It is possible for them to add up so that it becomes 0. So if it's possible to add up so that it becomes 0, then the momentum in the vertical direction can be considered to be conserved. It is possible. But now when you look at C, the vertical momentum are both in the same direction. If you were to try to add them up, they will always be a non-zero value. It will never be 0. Okay, so maybe I write another statement here. This one will always be non-zero. Okay, but the thing here is that the initial vertical momentum you already know must be 0 because you have no vertical motion whatsoever before collision. The initial vertical momentum is 0. So if your momentum is conserved in the vertical direction, the final momentum after collision must also be 0. So right now what you see here is that C will never be possible to be 0 when you look at the vertical momentum. So this diagram is actually not possible because it will tell you that momentum is not conserved. So that's why the question is asking you which diagram now is not possible. Which diagram doesn't show momentum is conserved. In other words, what they're trying to ask you is that when they say which diagram is not possible, it's like saying does not, it's like asking you which diagram does not show that momentum is conserved. Okay, the only one that doesn't show that is C. Now, if you try to repeat your analysis for part D, you will still come to the conclusion that it is still possible. You see, if I try to redo the resolution of the vectors, the one here can be resolved into this direction. The other arrow can also be resolved into this direction. So right now, if I just consider the horizontal momentum alone, this one can be non-zero. Yeah, sure, they're in opposite direction. It can be zero, but it can also be non-zero. Because if one arrow is longer than the other, you won't get a zero value. So this one can be non-zero. So it can satisfy the conservation of momentum in the horizontal direction. Now, then if you look at the vertical direction, this one can be zero. Because you see, both of them are in opposite directions. So provided they are the same length, same magnitude, you will end up getting zero. So it's a case of them being possible. The vertical one is possible to be zero. The horizontal one is possible to be non-zero. So this, if they are possible to be zero and non-zero, respectively in the vertical and horizontal direction, that means momentum can be conserved. So this diagram is also possible. It's just that C is not possible at all because it's clearly telling you that the vertical momentum is not conserved. Okay.
Yes, sir.
All right. So there's that part there. Okay, that was page 70. That was the second last question. So far, so good with this.
Yeah.
Okay. So you see, when you're doing the 2D collision questions, a lot of it is just based on the principle of you equating the total momentum before collision and after collision in a specific set direction. It's either horizontal in the X direction or vertical in the Y direction. Okay, but not necessarily it will always be in the X and Y direction. It could be some other direction, like in page 95. Okay. So are you okay with the question on page 90? So are you still writing something there?
Oh, no, I'm done.
Okay. So there are some cases where you don't necessarily need to have the you don't necessarily consider the momentum conservation just X or Y direction or horizontal vertical direction. You sometimes may consider in some other set directions. So let me just clear off this one. Page 95, did you manage to complete it?
Yeah, I did, but I didn't check the answer, but I got 200.
Got 200. Okay, so let's have a look at that. Yeah, March 2021, P1, 2. Answer for that is 200. Yes, answer should be 200. Okay, so here you are still doing principle of conservation of momentum because you see here now the momentum is not just in one direction, it seems to be in a diagonal direction. It seems to have a momentum in, yeah, basically you see that the momentum is not just in one direction, so it's a diagonal direction, therefore must be 2D momentum. Okay, so here they tell you you have a stationary firework that explodes into 4 different fragments that travel in different directions in a horizontal plane. The diagram shows the velocity and mass of each fragment. What is the speed v of fragment x? So now all the different cases that you have done so far, when it came to 2D collision, you were always considering the momentum in the X and y direction. That time we say that momentum in any direction is conserved. For example, in the x and y direction. But it's not always necessarily true that will be in the x and y direction. If you try to do the conservation of momentum for this question now, by trying to resolve the momentum in the x and y direction, you will have some problems trying to resolve them. One of the problems is that notice that you have no angles given, right? You see here, there are no angles given to you. You know that, yeah, there's 90 degrees, 90 degrees, 90 degrees, 90 degrees here, but they didn't really give you the angles. All right, what is this angle here? And what is this angle here? They didn't really give you the angle. You can't assume that it is split equally as 45 degrees and 45 degrees. So here, it won't be a wise thing to do to resolve them into x and y direction, because here you don't have the angles. So you don't consider momentum in the x and y direction. Okay, you don't consider momentum in x and y. Instead, you consider momentum in these directions. Okay, this one will make your analysis a lot easier. Okay, so if you know that this one is a stationary firework that explodes, you know that total initial momentum is 0 in any direction. Okay, this one is the first thing you know. Total momentum in n is 0 in any direction. So from there, you can also come to another conclusion saying that therefore total final momentum in any direction must also be 0. Okay, so if you already know initial momentum is 0, the final momentum must also be 0. So this in turn will tell you one thing: the momentum of the fragments after collision must be equal and opposite, so that they add up to become 0. Okay, so there's one thing here that you can actually deduce. Because the total initial momentum is 0, since the object was stationary, the total final momentum must also be 0 in any direction. So this will in turn tell you that momentum of the fragments after collision must be equal and opposite, so that they add up to become 0. So what you can then do here is something like this. Let me just remove all the unnecessary stuff. So what you can then do is that here, because you're more concerned with finding the unknown velocity v here, you just consider momentum along this direction. What you will know is that this momentum and this momentum will be equal and opposite along this direction. Okay, so what you just do is that you just say it will be 10 times 300 equals to 15 times v. Okay, you don't really need to bother changing the mass from gram to kg, because you see, if this is gram, if this is gram, and then this one is gram, the units will actually cancel each other off. So whatever unit you have here for velocity will follow the unit that you have here. Okay, which is just going to be meter per second. Okay, so here there's actually one hidden shortcut. You don't really need to change the grams to kg, because you see both sides of the equation have the same term. They will actually cancel each other off. The units will actually cancel each other off. Okay, so your V here would just follow whatever unit of speed you have here. If it is meter per second, your V will be meter per second. Okay, so you will just get 15V equals to 10 times 300, giving you V of 200 meter per second. Okay?
Yep.
All right, so that is for this one. This is for 2D momentum.